Hello everyone, I'm going to go through this lesson and we're going to talk today about complex numbers and imaginary numbers. So not all quadratic number equations have real number solutions, right? We talked previously about how we can't factor x squared plus a number. So for example, like x squared plus 1. This does not have real number solutions, right? We can't factor this. And so because x squared equals 1 has no real number solutions, we kind of have to compensate for that, right? Because if we did try to square root that, nothing squared is going to give us -1, right? 1 squared is +1. -1 squared is also +1. And so the way that we combat this problem is we have the imaginary unit I. And so all I is the square root of -1. Okay? It is, don't overcomplicate it, it is just the square root of -1. And so if we wanted to square both of these sides, if I is equal to the square root of -1, and we went ahead and we squared both sides, we would end up getting that I squared is equal to -1, right? So this would be our next step. And so this is actually a cyclical pattern, right? And so I is equal to I, right, which we know is the square root of -1. We just said that I squared is equal to -1. Now, if I took that I squared and I multiplied it by I to get I to the third, I would be doing, again, I squared times I. Excuse me. And so I squared is -1. So I'm really doing -1 times I, which would be -I. And then to do I to the fourth, I could do I squared times I squared, right? That is I to the fourth. Well, again, we said I squared is -1, so -1 times -1 would be +1. And so this pattern repeats. What that means is like I to the fifth would be the same as I to the sixth would be the same as I squared, which would be -1. I to the seventh would be the same thing as I to the third, which is -I. I to the eighth would be the same thing as I to the fourth, which would be 1. And the pattern goes on and on and on and on and on. Okay, so we can, you don't have to know that, but it is good to know that the pattern does repeat. So a complex numbered in standard form is a plus bi, where a is the real part and bi is the imaginary component. So we have imaginary numbers, that's a plus bi, where b cannot equal 0. And so what that means is basically it contains an I, that's what makes it imaginary. So 4 plus 5i is imaginary, 3 minus 2i is imaginary. They contain I, that's what makes them imaginary. Now, there's a subset of that, which is a pure imaginary number, and that is 0 plus bi. That's when we don't have a real component, and it's just the imaginary component. So examples would be like -5i, +5i, I, 2i, anything without just a real component to it. So you may have seen this little table before. This is the table of numbers, right? And so we've been working mainly in the real number frame. And so real numbers are numbers that, that aren't imaginary. Basically, they don't contain I. And imaginary numbers contain I. That's the big difference between them. And so we've mainly worked in the real frame, but now we're going to kind of go over into that imaginary frame. We also have rational numbers. Rational numbers either can be written as a fraction or have decimals that repeat or terminate. So we can say can be written as fraction. So -5, 0, 8/3, 9, 1/2, etc., etc. Whereas imaginary numbers cannot. These cannot be written as a fraction. I'm sorry, irrational numbers, not imaginary. So negative square root 5, square root 3, another really common one we see is pi. It's basically just a number that goes on and on and on forever with like no discernible pattern. Integers are positive and negative whole numbers. And so they're like negative 3, negative 2, negative 1, negative 100. 1/2 would not be an integer, though. We're just talking positive and negative whole numbers. Whole numbers are non-negative. Non-negative integers and natural numbers are positive integers. So the difference between those two is 0, right? So when I say non-negative, 0 is not negative. It's also not positive. So that's why 0 goes in with whole numbers, because it's not negative. But it doesn't go in with natural numbers because it's also not positive. Alrighty. So this is asking us to find the values of x and y that make each equation true. So in order for these to be true, imaginary parts have to be equal to imaginary parts, and real parts have to be equal to real parts. So on the left side, we see that 2x is real because it doesn't have an I attached. And so that would correspond with 8 because 8 is also real. So that means that 2x is equal to 8. And so to solve for x, we divide both sides by 2. So x is going to be 4. Now to find y, again, imaginary has to be equal to imaginary. So negative 20i would have to be equal to negative 4 yi. And so we're trying to get y alone, so we need to divide both sides by not just negative 4, but negative 4i. And so when we do that, on the left side, the i's will cancel, and negative 20 divided by negative 4 is 5. And on the right side, the i's will cancel, and so will the negative 4's, and that'll leave us with just y. So again, on the next section, real has to be equal to real, and imaginary has to be equal to imaginary. So the real portion of our left side is negative 6x, and the real portion of our right side is 2. And so to solve that, we divide by negative 6. So we'd get negative 2 over 6, which is going to reduce to a negative 1/3. And then we do imaginary equals imaginary. So 5i equals 10yi. So again, we want to get y alone, so we divide by 10i. So the i's will cancel, and we'll get 5/10, which will reduce to 1/2. So x and y can be fractions, and that's totally okay. Alrighty. So again, with this one, we do real equals real. So on the left side, we have 2x is real, and on the right side, we have negative 12. We do want to keep the signs in front of those terms when we set these equals. So 2x equals negative 12. We divide both sides by 2, and we'd get that x is equal to negative 6. And we do the same thing with the imaginaries, the ones that have I attached, right? Because we're setting imaginary equal to imaginary. And we divide by 5i. So when we do that, we're going to get negative 8 is equal to y. Alrighty, I'd like you to try D on your own. So again, we should set, this time we're setting negative 8y, which is our real piece, equal to a negative 2. And dividing by negative 8. So that should reduce to 1/4. And then we're doing 14i is equal to 7xi. And we divide by 7i to get that x equals 2. So it's not necessary that x is our real piece and y is our imaginary piece. It doesn't matter. It just means we can only set real equal to real and imaginary equal to imaginary. So this wants us to find the complex conjugate. And so complex conjugates are when we have a number, an imaginary number like a plus bi. And we have the same two numbers, but instead they're split by the opposite sign. So these are what we consider complex conjugates. Okay, so if we're looking for the complex conjugate, again, of the first one, we would do, if we have negative 3 plus I, we would do negative 3 and I, and we change the sign in between them. Now the complex conjugate of 5I, 5 is a pure imaginary. This is the same thing as if we had 0 plus 5I. So again, same two numbers, right? Because our real component there is just 0, and switch the signs. So if we simplify this, our complex conjugate is negative 5I. Our next one is going to be 2 plus 3I. And what would our last one be? Negative 8 plus 3I. Again, the only sign that's changing is the one in between them. And we'll talk about kind of why in a second. It's really, really similar to the fact that A plus B times A minus B is equal to A squared minus B squared, right? That difference of squareds. And so that's why we kind of use those conjugates. And we'll use those again in a second. So this question says, show that I root 5 and negative I root 5 are solutions. So what we're going to do is we're going to plug that into this equation. So we're going to plug in I square root of 5 in for x. So I square root of 5 squared plus 5 equals 0. So that tells us that I squared, and then the square root of 5 squared, which is just going to end up being 5, plus 5 equals 0. Now going all the way back to the beginning, we talked about how I squared is just negative 1. So I can replace that I squared with negative 1. So negative 1 times 5 plus 5, does that equal 0? Yeah, it would give us negative 5 plus 5 equals 0, and that is true. So we've confirmed that first solution. So then we do the same thing for the second one. Negative I root 5 squared plus 5. Again, we're plugging that second solution in. So a negative I times a negative I, again, would be a positive I squared, right? And again, square root of 5 times square root of 5 is just 5 plus 5. So we're back to where we were on that last path, where I squared becomes negative 1, and negative 1 times 5 is negative 5. Negative 5 plus 5 is 0. So we can confirm the other one as well. So the next question is 3I times 8I a real or imaginary number? Show the work that leads to your answer. So we would want to multiply these out. So we would do 3 times 8, which is 24, and then I times I, which is I squared. So again, we talked about how I squared we can rewrite as negative 1. So 24 times negative 1 is negative 24. Now, is that a real or imaginary number? Well, that one is real, right? There's no I attached anymore. So sometimes we can use I to get it to kind of cancel, and then we're left with a nice real number. So we kind of need I in order to hold a place to get back to a real number. All right, so we are going to simplify and write all our answers in standard form. That means we want to write them in that A plus BI form. So again, kind of like we talked about with the real can only equal real and imaginary can only equal imaginary, we can only combine reals together and we can only combine imaginaries together. So for this first one, we don't really need the parentheses here, right? Because if I distribute a plus sign, it's still going to be plus. And so then I would combine negative 1 with 3, and that's going to give me 2. And I'd combine 2I with 3I to get plus 5I. And so that would be my answer. Now, on the second one, because they're split by a subtraction symbol, I do have to be a little bit more careful here because I do need to distribute that negative. It's going to change the signs of everything behind it. So it's going to become minus 3 and plus 7I. But once I do that, I can combine my like terms like I did before. So 2 minus 3 is going to be negative 1. Again, we want to write that first because that's the real component. And then we'll do negative 3I plus 7I to get plus 4I. And so that would be our answer. Alrighty, so again, the next one, we're going to have to distribute any negatives or drop any parentheses. So we have 2I. We will have to distribute this negative. So minus 3 minus I. And then if I distribute a positive, it doesn't change the sign. So still plus 2 and minus 3i. So we'll again combine our constants first. So negative 3 and 2 gives me negative 1. And then we'll combine our i's. 2i minus I minus 3i is going to give minus 2i. Alrighty, next one. So the next one, we're going to go ahead and we're going to distribute out that negative I. So when I distribute it, I'm going to get negative I times 3, so negative 3i, and negative I times I, so negative I squared. Now again, like we talked about before, when I have an I squared, I can replace it with negative 1. So this double negative will turn into positive, and then I do still want to write it as, in that standard form. So I'm going to put that positive 1 out front, minus 3i. Alrighty, so then the next one, we have two terms, or two sets of terms, and so we're going to multiply this out similar to how we've multiplied out before, and we're going to use the box. So we're multiplying out 2 plus 3i times negative 6 minus 2i. So negative 6 times 2 is negative 12. Negative 6 times 3i is negative 18i. 2 times negative 2i is negative 4i. And then negative 2 times 3 is going to be negative 6i squared. Okay, so we can pull out that negative 12. We can combine those regular i's together. So that's going to give us negative 22i. And then we have minus 6i squared. And we want to think, can I simplify this? And I can, again, because I can take that negative 6i squared and I can turn that I squared into a negative 1. So that allows this to become negative 12 minus 22i, and then negative 6 times negative 1 is going to be plus 6. Then all I have to do is combine that negative 12 and that 6, so my answer is going to be negative 6 plus 22, minus 22i. Alrighty. So again, same thing, we're going to multiply out here. So hopefully we maybe notice that these are complex conjugates, but we're doing 3 plus 2i times 3 minus 2i. So 3 times 3 is 9, 3 times 2i is 6i, 3 times negative 2i is negative 6i, and then negative 2i times 2i is negative 4i squared. So when we take that out of the box, we'd have 9. Those 6 i's will end up canceling, and we'll get minus 4i squared. So again, we can turn that I squared into a negative 1. So it's really becoming 9 plus 4. And so our answer would be 13, which is kind of nice. It's nice and pretty. So again, we used imaginary numbers to get back to the real numbers. So going here, again, to do this, we would multiply it using the box. And we're multiplying 2 minus 3i times 2 minus 3i. So 2 times 2 is 4. And then we're going to get minus 6i. 2 times negative 3i is another minus 6i. And then negative 3i times negative 3i is a positive 9i squared. So we have 4, and then minus 12i plus 9i squared. Again, we should hopefully be seeing kind of patterns happening here, because again, I can turn that 9i squared into 9 times a negative 1. So it's going to be 4 minus 12i minus 9. So my answer will become negative 5 minus 12i. So again, going to the next one. So for this one, I would just go one at a time. So I'm going to start by multiplying these first two together. I multiply real with real and imaginary with imaginary. So that gives me negative 10i squared. And I'm still multiplying that by 4i. But again, I know that I squared is a negative 1. So really, that negative 10 times that negative 1 is going to be a positive 10. And then I'm doing positive 10 times 4i, which will give me 40i. So sometimes we have fractions, and this is where we're going to use that complex conjugate. So when we have imaginary numbers in the denominator, we don't want that. And so to get rid of it, we multiply by the complex conjugate of the denominator. So we do 1 plus I. And whatever we multiply the denominator by, we also multiply the numerator by 1 plus I. Again, it's got to be the same thing because we're technically multiplying by 1. So I'm going to start with multiplying out that numerator. So we're doing 2 plus I times 1 plus I. So 2 times 1 is 2. 1 times I is, you can write it as I or 1I. Then we'll have 2I, and I times I is I squared. So for that numerator, I'm getting 2 plus 3I plus I squared. Okay, and I still need to get my denominator, but I can go ahead and simplify that numerator if I want, right? Because I can do 2 plus 3I, and then I can turn that I squared into a negative 1. And again, I can combine that 2 and that negative 1 to get 1 plus 3I in my numerator. But then I need to go ahead and I need to multiply out my denominator as well. So I'm going to do 1 minus I times 1 plus I. So 1 times 1 is 1. 1 times negative I is negative I, or negative 1I. 1 times I is positive I. And then I times negative I is negative I squared. So I'm going to get 1. And then we should again see that those regular i's are canceling. That's what we want to happen. If something is not canceling, then we're doing it wrong. So we'll combine those negative i's, or that I and that negative I together, and they'll cancel out. And then we have minus I squared. So again, I can rewrite that I squared as negative 1. And so my denominator will just become 2. And technically speaking, we should split this up and make this 1/2 plus 3/2 I. I'm not going to pitch a fit if you do that or not. So this answer would be fine. I just want to make sure we can simplify that. All right, we're going to do it again. So again, we're multiplying by the conjugate. So what should I multiply by? I should multiply by 4 plus 3I. And again, what I do to the denominator, I do that exact same thing to the numerator. So again, I'm going to start with that numerator. And I'm doing 3 minus 2I times 4 plus 3I. So 3 times 4 is 12. 4 times negative 2I is negative 8I. 3 times 3I is 9I. And 3I times negative 2I is negative 6I squared. So for that numerator, I'm going to get 12. I can combine those i's together. So 12 plus I minus 6I squared. Again, that's just the numerator. Again, I can replace that I squared with a negative 1. So that's technically going to become a plus 6. And so I'm going to get 12 plus 6, which is 18, plus I for my numerator. But again, then I still need to do that denominator. So we do 4 minus 3I times 4 plus 3I. So 4 times 4 is 16. 4 times negative 3I is negative 12I. 4 times positive 3I is 12I. And then negative 3I times 3I is a negative 9I squared. So then we have 16, and those 12i's cancel, so minus 9I squared. Again, we can replace I squared with negative 1. So it's going to be 16 plus 9, which is 25. Again, you can split this up and write this as like 18 over 25 plus 1 over 25I. But I'm okay if you leave it as one whole fraction. All right, we'll do one more example of this. So again, here I should be multiplying by the complex conjugate, 4 minus 2I, on the top and the bottom. So starting with that numerator, we do 3 minus I times 4 minus 2i. 4 times 3 is 12. 4 times negative I is negative 4i. 3 times negative 2i is negative 6i. And then negative 2i times negative I is a positive 2i squared. So in that numerator, I'm going to get 12 minus 10i plus 2i squared. Then I'm going to replace that that I squared with a negative 1. And so I can combine 12 and that 2, and that's going to give me 10. So I'll get 10 minus 10i as my numerator. But then I have to do my denominator as well. So 4 plus 2i times 4 minus 2i. 4 times 4 is 16. 4 times 2i is 8i. 4 times negative 2i is negative 8i. And then negative 2i times 2i is negative 4i squared. So we have 16. Again, the 8i's cancel. So minus 4i squared. I can replace that I squared with a negative 1. So it'll be 16 plus 4. So that'll be 20. And one thing I can do here is all of these numbers are divisible by 2. Or I'm sorry, are divisible by 10. So I'm going to divide them all by 10. And that'll give me 1 minus, you can say 1i or I, all over 2. Just to kind of simplify it down. Alrighty. So whenever we have radicals like this, the second we see a negative underneath the radical, we can take out an I and we make that radical positive. So we do that for both pieces. Again, take out an I, then we can make that radical positive. And that's again because I is just equal to the square root of negative 1. So that's all we're doing there. So then we can multiply these two together. So we'll do I times I to get I squared. And then we'll do 6 times 15 underneath that radical. So 6 times 15. So we'll get I squared, and then we're doing the square root of 90, which does simplify, right? 90 is divisible by 2, that's 45. That's divisible by 3, that's 15. That's 3, that's 5, and 5 and 1. So we can take a 3 out. And underneath the radical, we're going to have 5 times 2, which is 10. And then again, we still have that I squared. But again, all I squared is a negative 1. So this simplifies to negative 3 square root 10. So that's why we want to take out those i's, because had we just multiplied from the beginning, we would have gotten a positive 3 square root 10, and that's not the same thing. Alrighty. So we're going to talk about, well, how do we solve with complex numbers? So starting with this first one, again, first thing we have to do is we have to get set equal to 0. So like before, we're going to add 16 to both sides. So this part is not new. Like before, we'll take out a GCF of 2, and we'll get x squared plus 5 when we do that. Now, if this was x squared minus 5, we could do a difference of squareds, and that would be okay. But the problem is it's plus 5, and so we can't do quite a difference of squareds. So the way that we combat this is we do a difference of squareds, right? We would normally do x plus the square root of 5, x minus the square root of 5. But because it's addition, we have to throw an I out front. So we do x plus I square root of 5 and x minus I square root 5. We do that, again, because this is addition. So we only do that when this is addition. And so then we can set each of those pieces equal to 0, and we can solve. Right? That 2 out front doesn't really give us anything. And so we'd subtract I root 5 from both sides and add I root 5 to both sides over here. So we'd get that x equals a negative I square root 5 and x equals a positive I square root 5. We also know this is true because, again, all the way back here, we talked about how I square root 5 and negative I square root 5 were solutions to this equation already. You can also write this as x equals plus or minus I square root 5. Alrighty. So again, this next one, first thing has to be equal to 0. So we'll add 6x to both sides. And we'll also add 7. So we're going to get 2x squared plus 6x plus 7. If you did try to factor this, it wouldn't end up working. So we do need to do a new parent function. Oh, I did want to change this. I want to change this to 8. Sorry about that. Change this to 8. Because otherwise it's really, really ugly. Okay. So we look at the first two terms and we can take out a 2 out of both of those. 2x. And we get x plus 4. So our zeros of that are going to be 0 and negative 4. Our axis of symmetry will be halfway between that. So our axis of symmetry is going to be at x equals negative 2. And so then we'll plug in to find our vertex. So we know that the x value of our vertex is negative 2, and we'll plug in to find our y value of that vertex. So again, we're plugging in once we get it set equal to 0. So 2 times negative 2 squared plus 8 times negative 2 plus 7. Okay, so negative 2 squared is 4, times 2 is 8, and then 8 times negative 2 is negative 16. Oh, I want to change this too. I know, I keep changing things. I'm going to make this plus 17. Sorry, guys. And so then y equals 9 when we simplify that. So our y value of our vertex is 9. So again, this is a shift left 2 and up 9. So we write this as x plus 2 squared plus 9. But then we still need to keep that 2 that was originally out front and bring that down. I know, we're doing a lot. All right, so to solve this with the difference of squares, we divide everything by 2. So we get x plus 2 squared plus 9 halves equals 0. So again, we normally do a difference of squares, but we have this as plus, and that's what kind of throws us off. But all that's going to change is that we need to include I. So that plus tells us we need to include I. So we're still doing the square root of these two terms, so the square root of the first term plus I times the square root of the second. And then the square root of the first term minus I times the square root of the second. So again, all that plus does, all the difference it makes is we're putting an I out front of that square root. And so when we set each of these equal to 0 and solve, we should get negative 2 and then plus or minus I square root 9 halves. It should look very, very similar to what we've done before. Alrighty. So again, we'll go here. So again, we're going to have to do another new parent function. This one does not factor. So we look at the first two. Out of those first two, I can take out an x. So we'd have x minus 6 plus 11. My zeros would be 0 and 6, which would make my axis of symmetry 3. So my vertex is going to be 3, and then I'll plug back in to find my y value. So I do 3 squared minus 6 times 3 plus 11. 3 squared is 9, minus 6 times 3 is minus 18, plus 11, that's going to give us 2. So my vertex is 3, 2. This is a shift left 3, up 2. So we'll write this as x minus 3 squared plus 2. And we don't really have to worry about a coefficient out front because there isn't a coefficient out front. So we'll go ahead and do this one. So again, difference of squares, but this time it's addition. Only thing that's changing is we're putting an I out front. So we're still going to do the difference of squares. We'll do x minus 3 plus I times the square root of 2, and x minus 3 minus I times the square root of 2. So my two answers are going to be a positive 3, and then plus or minus I square root 2. Alrighty. Again, got to be equal to 0. So we'll add 22. We'll have x squared plus 6x plus 22 equals 0. So we look at the first two terms. Out of both of those, I can take out an x, and I'll get x plus 6 plus 22. My zeros of that are going to be 0 and negative 6. And that will make my axis of symmetry negative 3. It's halfway between those. So then to find my vertex, we do negative 3, and then we plug that back in, right? So we do negative 3 squared plus 6 times negative 3 plus 22. So negative 3 squared is 9 minus 18 plus 22. So that should give us 13. So my vertex is negative 3, 13. And so we'd write this as, that's a shift left 3, so x plus 3 squared, and then up 13, plus 13. Again, we have that plus there. That's okay. All that means is we're still doing a difference of squares. We're just putting an I. So we do x plus 3 plus I root 13, and x plus 3 minus I root 13. So my answer would be negative 3 plus or minus I root 13. All right. Two more. Alrighty, so again, we look at those first two terms. If we're doing, again, that new parent function, and I can take out a 2x out of both of those, and I get left with x plus 4 when I do that. So my zeros of that are going to be 0 and negative 4. My axis of symmetry is halfway between those. It'll be at negative 2. And then to find my vertex, I plug in negative 2, and I get my y value. So I'm going to plug it into the second one this time, just for fun. So 2 times negative 2 times negative 2 plus 4 plus 12. 2 times, oh, didn't mean to put another parenthesis there. 2 times negative 2 is negative 4, and it'd be negative 4 times 2 plus 12. So negative 4 times 2, that's negative 8 plus 12, which is 4. So again, my vertex is going to be, that's a shift left 2, up 4, so x plus 2 squared plus 4. But then I still have to put that 2 out front. That is not going anywhere. So now to solve this, first thing I got to do is divide everything by 2. So that'll give me x plus 2 squared plus 2 equals 0. Again, all that plus does is it means we're going to include I. So we still do the difference of squareds. We do x plus 2 plus I root 2, and x plus 2 minus I root 2. So my answer will be negative 2 plus or minus I root 2. Alrighty, last one. First thing we should always do is check for a GCF. And there is a GCF. I can take out a 3. And so that leaves me with x squared plus 81. And so I don't need to do new parent function for this because it's already in a difference of squareds, but again, we have that addition. All that addition means is we're going to include an I. So we keep the 3 out front. We do the square root of the first term plus I times the square root of the second. Well, the square root of 81 is 9, so it's going to be 9I. And then the square root of the first term minus. So minus 9I. So my two answers there are just going to be positive and negative 9I. And that is the lesson.